All right, looks like we're live now. Had a couple technical flubs, just getting started a few minutes late. Let's see. So today's topic, we're gonna talk about graphing derivatives. So as a general overview that I put out here, we're gonna be talking about minimum and maximum, or as we call them, extrema. I'll also lay out some definitions for things such as inflection points and concavity. We'll also cover the mean value theorem and what it means for like derivatives and graphical representations of derivatives and functions and such. And then we'll also go through a couple functions and kind of visualize the function on the graph, see what the derivative of that function would look like, and further like a second derivative, for example. All right. First up, minimum and maximum. So generally looking at a function, we're kind of interested mostly in this interval that's in the center here. Up top, let's see. There we go. So that top point and that lower point. So just this graph, it kind of doesn't cover the entirety. We wouldn't, this function goes on infinitely as we choose greater values for x and, even lesser values for x. This function is going to go towards infinity. So we wouldn't really consider those points on the ends, the minimum and the maximum. Those would generally be, if you're only looking at that interval that we have here, those would be a minimum and maximum. We're more interested in things called local minimum and local maximum, which is to say at any point there is a maximum output for the function of x when you have x over a certain interval. So just looking at this interval, our local maximum is right here at the top, and our local minimum would be here at the bottom, because on this interval, basically conceptually what it means is that the derivative is changing sign. So from any point on this first point right here, anything to the left of the function on here is, the function is increasing, so the derivative is positive. Anything to the right of that point, save our other point, is decreasing. So I guess you could kind of put this into like three big areas where we would say anything on this side of the function in section 1, the derivative is positive, so it's increasing. Anything greater than that point but less than our other point in our little section 2, we'll call it here in the middle, the derivative is decreasing, the function is decreasing, so the derivative is negative. And then in our final little area, we'll call it area 3, our function is increasing, so our derivative is positive. So again, local maximum, local min, those are called, we call them extrema. So it's a pretty important thing to note. Extrema is talking particularly about local maximum and local minimum. There's also things such as inflection point and concavity. It's probably best to talk about concavity best. Concavity is concerned with the rate at which the derivative is increasing, or rather the sign of the derivative. So for concavity, we're actually going to, rather than split it into three pieces here, we'll actually just imagine like a giant line basically on the y-axis. And we would say anything on the left side of the y-axis here is concave up because it's kind of like curved, it's concave down. So it's curved downward like that. Basically what that means is that the second derivative is negative. And then on the right-hand side of the y-axis, we have our function is concave up. So there's two options for concavity. It's either concave up, concave down. In this particular function that I have graphed here, it's concave down on everything to the left of the y-axis and concave up on everything to the right. So we'll say, oops, concave up, and we have concave down. All right, and then so once we understand concavity, we know that there's a thing called an inflection point, which is to say, at some point it goes strictly from being concave up to concave down. And that point, in this case, is right at the origin at 0, 0. That's called an inflection point. Inflection point. And we'll explore that a little bit more as we go into detail about, for example, graphing the derivative and graphing like a second derivative. It'll be a lot more clear what our inflection point is. All right, so the other thing we'll go into a little bit more detail about is the mean value theorem. Literally, it states if a function is a continuous function on the closed interval from a to b and differentiable on the open interval from a to b, there exists a point c in ab such that the derivative of the function of c is equal to quantity function of b minus function of a over b minus a. So kind of a lot to unpack there. One important little detail is that there exists a point C where this is true. That means that if we can apply the mean value theorem, there must be at least one, and it's possible that there's two. So going back to this function again, let's say we choose a as a is the origin, so this point right here, that's our a, and we'll choose something up here to be our b. Basically what the mean value theorem says is that we can draw, assuming this is a continuous function on a closed interval and it's differential on an open interval, which we know is true. This secant line, basically there is a point C from, let's call that basically 3, from 0 to 3. There's a point C between 0 and 3 such that the slope of the line, so the slope of our function is equal to the slope of the tangent line. Or I'm sorry, there is a tangent line such that that slope is equal to the secant line between a and b. So we would say it'd probably be like right about here. If we draw a line tangent, it'd look about like that, maybe a little bit better, a little bit clearer, but so these would be parallel, I guess you could say. So such that the derivative of this, the slope, is equal to the secant line there. And as I said, there can be multiple points C. So if we choose something different, such as -3 as our A and +3 as our B, so we would have this point over here, and we'd be looking at this point and this point, and we just kind of extend our line here, and we'd see there's actually 2 points. Since it crosses back over our line, there's actually a point up here on the left side with an equal slope. So there'd be 2 C's where the mean value theorem shows us that there's two spots where the slopes are equal to a minus b, or rather the slope of the secant line between a and b. All right, and then the last thing we'll cover is we'll visualize some derivatives. We'll look at a couple graphs, and we'll try and plot the derivative, the second derivative, and we'll use some of our knowledge on extrema and concavity inflection points to kind of, get a full picture. All right, so kind of covered this a little bit already, but let's say we have the function negative x squared plus 3. Something about the minimum and maximum is that you'll notice that the derivative is like the rate of change. So in this case, our maximum and minimum are supposed to be critical points, you could call them, which is to say, when the derivative of the function is 0, when it's not changing, that's where our maximum is going to be. So that information basically tells us that if we have a function, if we take the derivative of that function and set it equal to 0, whatever x we plug in, so such that the function is equal to 0, that's the location of the min or the max. So in this case, we'll just do a simple little differentiation. So the derivative of negative x squared, just do a simple power rule. We get negative 2x plus a constant. So the derivative of a constant is 0. So, oops. Ooh. Oh. Wipe that out real quick. Whoopsie. All right. So, as I was saying, the derivative of a constant, 0. We got the derivative of negative x squared as negative 2x. So this is a pretty simple example. The maximum happens just to be at 0. So we would set this equal to 0. We'd say negative 2x equals 0, and it's pretty obvious. We plug in 0 for x, we'll get 0. So we would say that point is our maximum. And well, first of all, we would call this point a critical point, and we would, like, if we didn't have the graphical representation, and we wouldn't know whether or not this is a minimum or a maximum. So we want to actually test values for x greater than or less than 0. So, for example, looking at this graph, we know that the slope is positive for any value less than 0, and the slope is negative for any value greater than 0. So let's say we have our derivative, which is negative 2x, and we plug in any negative number. Then we're going to get a positive number, because negative 2x times a negative number is going to give us a positive number. Let's see. So if we had a positive x, it would be a positive times a negative, which would give us a negative, so we would know that our slope is negative. So let's see. We'll write out f prime of x equals, scratch that. We'll do f prime of negative 1, because that would be we know our critical point is 0. So we'll choose a point to the left of our critical point, which is negative 1. We plug that into negative 2x, and we would just get 2. So we know that our derivative is 2 on the function at negative 1, so it's positive. So we know it's positive, and then if we have f prime of 1, it would be negative 2. So that would have a negative slope. So our critical point, 0. Let's say this is our critical point. You know, we have like a little box representation where this is, let's get rid of that real quick. Give us a little bit more space. All right. So 0, anything less than 0, it's going to be positive. Anything greater than 0, it's going to be negative. So that's generally the representation you want to do to kind of get an idea, especially if you don't have the graph in front of you, of whether or not it's a minimum or a maximum. All right, so here's a little bit slightly more complicated example. So just going off strictly of the graph, we would know that we have a local maximum about here, local minimum about here. Actually, this is the same as the example problem up above. So as far as first derivative is concerned, we kind of have 3 sections of our graph. The derivative is positive in this section, it's negative in this section, and it's positive again in this section. And we know that we have an inflection point here, so that'll be a point of interest if we go a little bit further, go a little bit deeper into this problem. But I think that's a good start, is just looking at this graph. We know pretty obviously kind of what the derivative is going to look like. So let's just go ahead and calculate that derivative. So we have x cubed minus 7x, so just a power rule. That'll give us 3x squared minus 7. All right, so the points at which this is 0 let's see. So f0, oops, that's not what I want to do. So we'll bring this up here. We'll say 3x squared minus 7 equals 0. So anytime this is true, we're going to have a point at which the slope is 0 on the graph, which is going to have to be, assuming there is a change in slope, there is going to be either a local maximum or a local minimum. So do a little bit of algebra. We get x squared equals, x squared equals 7 over 3. And since it's squared, we know that basically this could be, x could be plus or minus the square root of 7 over 3. So that means we have two values, or two critical points that we're interested in. One at positive root 7 over 3, one at negative 7 over 3. So we would kind of draw like a little line chart. Let's see. We'll plot our little points. We'll have positive root 7 over 3 and negative root 7 over 3. All right, so if we didn't have this graph, we would have to do this visualization to kind of see when the slope is positive and when it's negative. All right, so any point less than root 7 over 3. So let's just choose, for example, negative 3. We plug that into our derivative, so f prime of negative 3. Let's see. So that'd be negative 3 squared, so that'd be 9 times 3, 27. 27 minus 7 equals 20. So that's a positive number. So we know that any value less than negative root 7 over 3 is positive. So our function is increasing at any point less than negative root 7 over 3. All right, a pretty easy point to choose in between these is 0. Plug 0 into our equation for the derivative. So we'd have f prime of 0. That's just 0 minus 7. So we get minus 7, that's negative. So anything in between these two values is negative. Anything greater than root 7 over 3, we'll just choose 3. So we'll have f prime of 3. That would be, that's again 27 minus 7, which is 20. And you know, we see in this graphical representation, it goes plus minus plus. And we found through our critical point analysis, it goes plus minus plus. All right. Let's see, mean value theorem. So we did a couple short little example earlier here. Basically the same graph, but we can do more of like a less of a graphical approach, more of an analytical calculus approach. So the definition of the mean value theorem, or really the equation that gives us, is for that point C. If you evaluate point C in the derivative of the function, it should equal the function of b minus function of a over b minus a. So in this case, we do have the function written out. Let's pretend we don't have the graph. So we want to find a point C in this equation such that, you know, from b to a, basically, that secant line is equal to the slope of our tangent line at C. All right. So first we'll just go ahead and evaluate, well, we have to choose, I suppose we have to choose a b and an a. So we want to go from a to b, so let's just choose a is negative 4, so it'd be down here. And our b is positive 4, so it'd be up here. All right. So we'll have our a equals negative 4, b equals positive 4. And then we'll go ahead and go f of a equals, so negative 4 cubed, that would be negative 64. Negative 64 minus a negative, so it would be plus 7 times 4, which is 28. All right. So that would give us a negative number. Let's see. 4, 6, 36. Yeah. All right. So f of b, let's see. So we would have 4 cubed again. So it'd be a positive, but this time it'd be a positive 64. And it'd be minus 28. Oh, I'm sorry. That's why this is not making sense. Negative 36. And this will give us positive 36. All right. So that, just looking at our graph, that makes sense. Just because if you look at the y-axis here, it's somewhere between 32 and 40, which 36 is. All right. And then b minus a, let's see. So b is 4, a is negative 4, so b minus a would just be 8. So that would be, what would that be, about 4.5 for our right-hand side of the equation. No, we have to subtract each of the functions. Yeah, so it'd be 72 over 8. So it'd be 9, actually. All right, so we do function of b minus function of a. We'll just do it real quick. So 36 minus a negative 36 would be plus 36. That is 72. And the bottom is 4 minus a negative 4, which is 8. 72 over 8 equals 9. All right. So now we want to find a c such that the derivative of the function, original function, is equal to 9. And it should be 2 points, since we showed earlier that, you know, the mean value theorem is concerned with this secant line and a tangent line that has an equal slope. So we should have 2 of them. But we can go ahead and calculate that. So let's see, we'll white out some of this that we don't need. Don't need that. Don't need that. All right, so we know 9 is our right-hand side of the equation, so we'll put 9 up here. Equals 9. All right, so we'll calculate a quick derivative of our function here. So we have f prime of x equals, we'll do a power rule for x cubed, so it would be 3x squared minus 7. All right, so we want our 3x squared minus 7 to equal 9. So we'll do a little bit of algebra. 3x squared equals 16. X squared equals 16 over 3. So x equals plus or minus root 16 over 3. All right, so root 16 is 4. Root 3 is a little bit less than 2. So that should be about 2, which, looking at our graph, looks about correct. We have about 2 here and a negative 2 here, since it's plus or minus. So that's how we would use the mean value theorem to, if we didn't have the graph, we could calculate exactly where those C points are, where the let's see, the interval, the slope of the interval from A to B would have tangent lines that are equal to the secant line from A to B. All right, we'll do a couple examples to visualize basically what derivatives look like and kind of how to get an idea of just looking at if we have an x, a function at some complex polynomial, or, in this example, something simple but has a high power. So we have a function of x, and this graph is red, it looks like. So we would say this one is red. So the derivative, here, let's look at our red function. And think about the derivative a little bit. So again, the derivative is the rate of change. So anywhere on the left side of 0, left side of the origin, this red line is increasing. And is getting increasingly less increasing, so it's not as steep, but it is increasing for that entire interval from 0 towards negative infinity. And then on the other side of the origin, it's positive. So that's why we have this representation, this blue curve of x squared, because the derivative is actually positive for this. It does hit 0, but it actually goes from just being positive to being 0 for one instantaneous point, and then it goes increasing again. So that's why our f prime of x, the graph of it, is always positive. It's always on the top side of the x-axis, I guess you could say. And then we can further take a derivative. We would have 2x, so derivative of x squared is 2x, and that's linear. And basically what that means is it's constantly negative on the left-hand side, it's constantly positive on the right-hand side. So the derivative of that function would actually have a linear representation rather than a curve. All right. So here we actually have a piecewise function. If you're familiar with the function of the absolute value of x, so the function of x can never be positive because the absolute value by definition is always going to be positive. So what that looks like on the graph is basically all of our function is going to exist entirely on the positive side of the x-axis. I'm sorry, the positive. It's going to be above the x-axis. It's never going to be negative. Y is never going to be negative if y is equal to the function of x. So what that means in terms of like a derivative is, well, actually, let's talk about the way this function looks first. So it's equal on each side of the y-axis, more or less, but not concerned with derivative. If we were to reflect this function over the y-axis, it would be equal. But we're actually interested in the derivative, so we know that everything on the left side of the y-axis is decreasing, so it has a negative derivative. Anything on the right-hand side of the y-axis has a positive, or is increasing, so it has a positive derivative. So we would write the function, or the derivative of x, as a piecewise function, because whenever x is greater than 0, it's going to be positive, so it's going to be 1. Whenever it's less than 0, it's going to be negative 1. Something to consider, we earlier talked about the mean value theorem, and the main reason why the mean value theorem does not work in this case is because we have a point on our function that is non-differentiable. It's this corner right here at the origin. Basically, that point is non-differentiable because there isn't, you can't take the derivative of that. It's, it doesn't have a rate of change since it's like a corner like that. So if we were to choose, A to be -1 and B to be 1, we actually don't have a point on this graph where where I guess the derivative is exactly 1. All right. So here we'll do a little bit more complicated example where we're just given a graph and we kind of want to try and figure out exactly what's going on. So first things first, we want to find our extrema, our critical points, and we also want to find points of inflection. So also we're assuming that this graph kind of goes on to infinity, so it goes upward like that. It doesn't oscillate. It's not like the sine function or anything like that. So this goes that way, that goes that way. All right, so we would have a local minimum right here at this low point down here. We would have a local maximum up here. And it's a little bit difficult to see, but anything from 0 onwards, anything greater than 0 is concave down. Anything less than 0 is concave up. So we actually have an inflection point at the origin. All right. So first we'll go ahead and divide our graph into a bunch of sections. All right. So we look at anything less than, it looks like about negative 80. Anything less than negative 80, that's going to be, we'll talk about the derivative f of x. So the derivative is going to be negative whenever it's increasing. Whenever our function is decreasing, it's going to be negative. It'll be positive whenever our function is increasing. So from left to right, this is decreasing, so our f prime of x is negative. Anything greater than negative 80, between negative 80 and 0, it'll be positive. Anything from 0 to positive 80, it's still going to be positive. So our inflection point doesn't quite matter just yet, but it will. And then anything greater than about 80, it's going to be negative. All right. So with this, we're going to try and graph f prime of x. So it might be a little bit hard to see, but I do have the function there. So we have, let's see, anything from about here back should be negative. Anything from about here forward should be negative, and anything in between these points should be positive. All right, so basically what that means is, so our derivative changes sign at the points negative 80 and positive 80. And when it changes sign, that means that we're going to have a local maximum or a local minimum, which means the graph of the derivative is going to hit 0. So we're going to have a point at 0 here for the f prime of x at negative 80 when there's a local maximum or minimum, and again at positive 80. So we know that the graph of, let's see, f prime of x, so it has to be 0 at negative 80 and positive 80, or around those points, just looking at based off of a visual aid. And we know that anything less than this is going to be negative. So it should be coming upwards like this. And we know anything greater, no, that's not right. Let's see. So we'll check out, let's see. So our slope is negative. So yeah, anything down here, it should be less than x. So it should be below the x-axis is basically what that means. And then once it's increasing, our y values or our f of x will be positive. So anything greater than negative 80, less than 80 is going to be positive. So it's going to be above the x-axis. And that means anything greater than 80 is going to be, again, negative. So we know that our function is increasing everywhere from negative 80 to about 80. So it should be positive. And we'll go back to our inflection point that we found. And basically what that means is it switches from being concave up to concave down, which means the second derivative switches signs. Basically what that means is that we want even though it's increasing, we want it to be decreasingly increasing, rather. So that means that we know we have a inflection point somewhere on the y-axis. So our function our f prime of x should look something like this. So we have that inflection point on the axis where our, the slope of our slope, I guess you could say, goes from being positive to negative. All right, and then, so that would be the graphical representation of f prime of x. If we wanted to go further, we could actually calculate the derivative of this as well. So we would say anything on the left side of the y-axis is positive. So it's increasing. Everything on the right-hand side of the y-axis is negative, so it's decreasing. So we know that our graph of f double prime of x is going to be positive whenever x is less than 0, and it's going to be negative whenever x is greater than 0. So f prime of x will look a little bit more like this. All right, and that makes sense because we have an inflection point here on the y-axis. It correlates to a crossing of the origin here, f double prime of x. And a general good strategy for these is you want to find the critical points, which in this first case we found at negative 80, positive 80, and we had our inflection point where our function changed in concavity. And you basically, if you don't have the graph, you want to write out like a line graph. This is especially true if you have just a function and you don't actually have the graph. So you plot out your critical points, which would be negative 80. We'd have 0. We'd have 80. And if we were given the function, we would have f prime of x equals something. And then we would plug values that, for example, are less than negative 80, between negative 80 and 0, between 0 and 80, and greater than 80. And in our case, let's see, so we have values that are less than negative 80 that we plug in for f prime of x would be negative. Values between negative 80 and 80 are going to both be positive. And values greater than 80 are going to be, again, negative. All right. So I think that's a pretty solid overview of what's going on when we're graphing derivatives of, fancy polynomials or even just simple polynomials of degree 3, 4, etc. All right. So we'll go ahead and maybe just draw out a couple extra little examples, kind of get a better idea of the best way to tackle these problems, kind of understand what's going on. Let's see. Let's say, for example, we have a function that looks like this. It has a maximum at negative 3 and 3. It hits the origin at 0, 0. And it is decreasing, increasing, decreasing, increasing, decreasing. So this is f of x. We assume it is true for full domain negative infinity to infinity. So we would say that our f prime of x, well, first of all, our critical points are all those points that we found. A change in inflection, local minimum, local maximum. So in this case, since we have 2 local maximum, 1 local minimum, we have 4 sections. So we have section 1, section 2, section 3, and a section 4 over here. All right, and we'll go ahead and put f prime of x over on this Cartesian plane. All right, so any value that is, for any value of f of x that is less than negative 3, we're going to have a positive slope because that's positive over here. So this should be positive. And then we know that since we have a local maximum on the function, the slope at that point is going to be 0. So our f prime of x is going to be 0 at negative 3. We can go ahead and look forward and see for our local minimum, we have a point 0, 0. And our other local maximum, we have, it's going to be 0 when x is 3. All right, so our function should be increasing anywhere less than negative 3. So it should be positive. Whoops. All right, so we have our f prime of x should be positive, so it should be above the x-axis. whenever we have a value of x that is less than -3. Let's see, in our second section of here, the f prime of x is decreasing, so we'd have a negative f prime of x, so this should be negative. An extra little thing we have right in here, and in here are inflection points. So we assume that anywhere from, let's say, about -2 and 2, our function switches from being concave down to concave up, back to concave down again. And that will give us our local minimum or maximum of our f prime of x graph. So we know for values greater than -3 for f prime of x, our function is negative, so it should go below the x-axis. And then the inflection point is at -2, so it should have a local minimum at -2. So we'll put our little local minimum here, and it goes back up to 0. And again, third section, we have our slope is positive. Put a little plus here. We have an inflection point at f of 2. So we should have a maximum at 2. And then we know that our slope is positive, so it's always going to be above the x-axis. So it should look something like this. And then in our fourth section, our slope is negative again, so we'll go below the x-axis on f prime of x. So it'll go negative. And we can go even further, and something interesting about these is just looking at the graph and seeing how many minimum, maximum, how many inflection points there are. You can kind of see what the degree of our polynomial is. So for example, f of x has, let's see, it has 2 points of inflection. It has 3 extrema, 2 max, 2 min. I believe that means this would be, so the degree of f of x, I believe, is 4. So it should be 1 more than the number of extremas. So the degree of f prime of x should be 3. And just going off of what we know about what the graph of x cubed versus x squared versus x looks like, it seems to make a lot of sense. So the degree of f of x, basically that means that this, our original f of x should have an x to the 4th as the greatest power, or the greatest function, the greatest variable. All right, I think that about wraps it up. I'm definitely open to do some more examples. I'll stick around, see if anyone has any questions that they like some help with, or something I can elaborate on. I'll go back through a couple things, make sure I thoroughly explain them all. So we have concavity, concave up, concave down. The point at which our function switches from being concave up or concave down is our inflection point, which we found to be at the origin here on this first function. Our extrema are our local min and our local max. Those are the points at which the derivative changes sign, so it either goes from being increasing or decreasing. We went through the mean value theorem. I suppose we could do another example of just calculating the mean value theorem with when we're given a function. So I'll white out a couple things here, give myself some space. All right. So let's say we have our interval is, come on. Let's say it's -3 to 2. So A is -3, B is 2. So that will generate a secant line. And we want to find a point on this graph C such that the derivative of their function, or rather the slope at point C, is equal to this tangent line. So, I'll draw that guy again. All right, so we should have some point C up here where the tangent line to our function is parallel to that secant line. And using the graph, we can kind of take a pretty good guess. It's going to be probably less than 0 and greater than -1. But we can use our mean value theorem to find exactly where that point is. So let's see. First, we'll evaluate our function at a and b. So f of a, so we chose -3 to be our a. So the opposite of -3 squared would be -9. You add 3, you get -6. And then we have our function of b, which is 2. So it'd be -4 plus 3, so it'd be -1. And just looking at our graph makes sense. -6 is right here. -1 is right about here. So we have our points relative to the y-axis plotted pretty correctly. All right, so then we'll go ahead and look back at our mean value theorem equation. So that should be f of b minus f of a over b minus a. So that would be -1 minus a -6, so that would be +6 over b minus a. So that'd be 2 minus a -3, so that'd be 2 plus 3. So actually that's pretty straightforward, it's 1. So the slope of this secant line from A to B is exactly 1. That's interesting. All right, now we'll go ahead and try and figure out where that point C is. So we have to find the derivative of our function, which we know is -2x. So that'd be f prime of x equals -2x. And we want to find the point at which that is equal to 1. So when is -2x equal to 1? Just do a little bit of algebra. We would see x is equal to -1/2, which is exactly halfway between -1 and 0. All right, so we would say that c equals -1/2. And in the case that we wanted to find the exact coordinate of this, we would just plug in our c into our original function. So we're going to find, the ordered pair at which c is located on the Cartesian plane. So we would plug -1/2 into our original function. So that would be, let's see, so that would be -1/4 plus 3. That would be 3 minus 1/4. That would be 11/4. And that would be our y-coordinate for c. So c would be -1/2, comma 11/4. That would be the exact point at which c is. So c is right there. So that's the general strategy for the mean value theorem that gives us a point on the graph. We'll have a tangent line with a slope equal to the secant line between a and b on that interval. All right. Let's see, we did a little bit of min-max calculation here. So again, if you want to find the local max, local min, you would take the derivative of the original function and set it equal to 0, which is what we did. And that would give us our points at which we have our local min and our local max, because this is f prime of x. So we have our 3x squared minus 7x. We set that equal to 0. Since it's x squared, we have a positive and a negative value for x, so we have two different values for x. And then we would, if we don't have the graph, we have a line plot that we put out where we put our two critical points, negative root 7/3, positive 7/3, and find values that are greater than, less than, between those values, and see whether or not that gives us a positive or a negative output, and that'll tell us whether or not our function is increasing or decreasing. Obviously, anytime something is increasing and then it goes decreasing, that's going to give you a max. And anytime it's decreasing and then it goes to increasing, that's going to give you a minimum. We have our mean value theorem with our secant c's, our example where we had two c's, because we chose we chose an interval in which there were two min and two max. And the function actually has to cross over that secant line twice, so it's kind of like there's almost two secant lines just added together, which is why we have two c's here. We did a little bit with just kind of visualizing the derivative of a third degree polynomial. See how it goes from this red line to the blue line, and it eventually becomes linear after we've taken a second derivative. We saw that piecewise functions are non-differentiable, or well, if a piecewise function is non-differentiable, it usually will be. We said that there's a non-differentiable point, so if we chose an A and a B that are on opposite sides of this non-differentiable point, the mean value theorem would not be true because it's only concerned with intervals from A to B that are differentiable and continuous. And then we did a slightly more complicated problem. So again, we did that little line graph where we choose values greater than or less than our extrema, and that'll give us an idea of, local min, local max, concavity, inflection points, etc. All right, I think that about wraps it up. Go ahead and sign off for now.